Welcome to the 18th lecture. We are studying stochastic processes, and in this lecture, we'll explore how we implement n-step probability using recursion. Recursion is a technique in which we apply the same formula step by step by decreasing the value of n unless we reach to the base value. So the same function is invoked or used or called again and again from within the function. That is how the recursion is implemented. We'll try to explore this operation with the help of an example we have already solved. This is a Markov chain or a transition probability graph TPG of a process where we have only two states 1 and 2, and these are the probabilities, right? The transition probabilities. Now let's move to the formula for n-step probability Rij of n that we studied in a couple of lectures before. This n is the time n, and this j is the targeted state where we want to be at time n, and I is the initial given state at time t is equal to 0. So this gives us the probability of being at state j at nth time step, given that at time 0 you are at state I. This is implemented with the help of a recursive formula, a formula that is based on recursion, that we call the same Ri R for n minus 1, and we implement it like this, that suppose we want to find out the probability of having state j at time n, given that the state is I at this initial time. So we mark here a time n minus 1, and we say that what is the probability that the state at n minus 1 is k, where k contains set of k is a member, or k belongs to the set of all possible states in the chain. We have two states here, and then we apply the r on n minus 1 here. So this small portion is replaced with some pkj. This is pkj. This portion refers to a probability pkj, and the same r with the difference that now we'll calculate it for n minus 1 is this time. So this is how we decompose this Rij formula into Rij of n formula into n minus 1, and we keep going unless we reach the base value. And this formula is defined for n greater than 1, whereas Rij of 1 is simply the transition probability Pij. Right, this is R. R11 of 1 is P11. In this chain, R11, the probability of landing at 1, given it is at 1 initially, is 0.8. So let's solve it for R11 of 2. So this is time n. That at time n is equal to 1, that this means that this is the time. This graphically means that I am at state number 1 at this time, and at the next time interval, what is the probability that I am at state 1? This means this. But what does this mean? R11 of 2. This means that I am at state 1 at time 0. I don't know where I was at time 1, but what is the probability that I'll be at state 1 at state number 2? Here I can be at state number 1 or 2, I don't know. But what is the probability that I'll be at state number 1 at time 2? This is we call R112, RIJN. Right. So we'll have I here as 1, J is a 1, and N is 2. So we'll use the same formula that we derived here, that we have wrote here and derived in our earlier lectures, where I is 1, J is 1, N is 1, and K is 1 to M. What is M here? M is the total number of states, and in this example we have small m is equal to 2 because we have only two distinct states here. The state space contains them. So putting all these values here, we come out with R1K of 1. This means while we are computing R11 of 2, we come across R1K of 1. This is how we implement recursion. And we will put the values, both values of K, we come out that we reach to an expression where computing R11 of 2, while computing R11 of 2, we need R11 of 1 and R12 of 1. Right. So for one lesser value of n, we need these two values. So we must have these two values before we compute this R11 for time step 2. And we know that R11 of 1 is P11 because R's are defined for n's greater than 1. So we compute this R11 of 2. Right, R12 of 1 is the same because R's are defined only for n greater than 2, for greater than 1, 2 or above. So R12 of 2 once again will implement the same formula here, and we know that this, to compute R12 of 2, we need R1K of 1, one previous R. So this is the basics of recursion. Find the value at 2, we need its value at 1. Right, and then we implement by putting the values of K. K is from 1 to 2 because we have two states in the state space here. Putting all these values take us to this value 0.24. Right, what is R11 of 3? We know that R11 of 1 is P11, R11 of 2 at time 2, we computed that to be 0.76. But what does this R11 of 3 means? This means that now we have this time 1, 0, 1, 2, 3. I am at state 1 at time t is equal to 0, and I want to compute the probability that I am at state 1 at time 3. And I don't know, I can be at 1 or 2 here, I can be at 1 or 2 at these two time steps, I don't know. But I want the probability of being at state 1 at time t is equal to 3. So to implement that, we once again apply recursion. R11 of 3 requires R1K of 2, the value of R for one previous value of time. And we require R11 of 2, R12 of 2 when we put the values of K, and we have computed both previously, and we put that and we reach a value here. So when I put these values of R11 in a table versus N, I observe that the values decrease and they are set to settle. They are going to settle at certain value. They are going to saturate us at a certain value. So most of the times we see the values settle in Markov chains. These R's, as n increases, as n increases, all r's are going to settle. What's about the other r's? There are three more r's here. R11 that we have plotted versus, and here there is R12, R21, and R22. How can they be plotted? For that, I have written a MATLAB code for you, for which I'll share that code too. For that, we have to enter this transition probability matrix or state transition matrix here. This is point 8, point 2. Why we have written it? Why was it written to be point 8.2? Because from this chain we write P11 0.8, P12 is 0.2, P21 is 0.6, P22 is 0.4. So we have written this matrix computed from the state transition graph or transition probability graph of a Markov chain. That's all. And rest of the work is done by this code. If you want to understand this code, you go through it, you will probably understand that I have tried to compute the steady state probabilities versus increasing n for all these r's, r11, r12, r21, and r22. So if I run this code, it takes me to a set of graphs. It was computed for this matrix, and these are the graphs. This is R11, this is R12, this is R11, R12, R21, R22, and we see that the value of R11 decreases as we know, and it settles down to 0.75. R12 settles down to 0.25. R21 settles to increases and it settles to 0.75, and R22 settles. So the steady state probabilities in Markov chains tend to settle themselves as as the time n increases. I have I have generalized this code for any size of for any given Markov chain. So here's another Markov chain which contains four states, and this is the state transition matrix for this chain. Right. If we run this code, it will be run for this matrix. This is the state transition matrix for this Markov chain, and these are the graphs. It's R11, R12, R13, R14, this is R21, R22, R23, R24, and this is finally R44. You can also play with this code by changing the value of capital N here. Capital N means the number of time steps I want to test this, for the number of time step for which I want to test this code. So let's make it 20. So now it will run for 20 iterations, and this is how it works. So for 20 iterations we see all the values of r, they're going to settle. Either they increase or they decrease, but they tend to settle. And for certain states, the value of r is either 0 or of 1. But if the state isn't if it is a transient state, it will be like this. It will be moving somewhere from a value and will be saturating in as the n increases. For n is equal to infinity, even that will be the same. So it decreases, becomes 0, and then it remains 0. So this value increases, settles at 0.65, and then it remains 0.65 as the n increases. And even for n is equal to infinity, this remains the same. So going saturate at different values. So you are encouraged to play with this code and try different other combinations, and you can try it for different values of Markov chains you can think of. But you should be careful that the state transition graph, the state transition matrix or transition probability matrix of a Markov chain should have each row sum to 1, like we have here. 1, 0.3, 0.4, 0.3 is 1. So you can try any matrix with this code and see the states going having a steady state switching to a steady state probability, but you should be careful that each row should sum to 1. Right. That's all for this lecture. We'll continue studying Markov chains in our upcoming lectures. Thank you.